We will now look at solving recurrence relations. So given a sequence that is recursively defined, it is often helpful to know an explicit formula for the sequence, especially if we need to compute terms with very large subscripts, or need to examine general properties of the sequence. The most basic method for finding an explicit formula for a recursively defined sequence is known as iteration, and it works as follows. If we're given a sequence that is defined recursively, we start from the initial condition and calculate successive terms until a pattern becomes apparent. It is at this point that we can then guess an explicit formula. As an example, let's consider the recursively defined sequence given by a sub k is a sub k minus 1 plus 2, and an initial condition of a naught is equal to 1. So what we need to do is start with a naught equaling 1. Now let's just calculate successive terms. So a1 is a sub k minus 1, so a naught plus 2, so this is 1 plus 2. Then a2 is a1 plus 2, so this will give us 1 plus 2, then plus 2, so it's 1 plus 2 times 2. A sub 3 is a sub 2 plus 2, so we get 1 plus 2 times 2 plus 2, so this is 1 plus 3 times 2. Right, and we can keep going, but a pattern has now been established. So our guess is that a sub n would equal 1 plus 2 times n for all n greater than or equal to 0. Now, it is important at this point to note that this is purely a guess. We are not sure if this is actually a solution. In order to guarantee its solution, we have to prove it using induction, and we will actually go along those lines a little bit later in this video. So for now, we're just going to stick with this guess. Right, so the key to iteration is pattern recognition. So this type of sequence, in which each term is equal to the previous term plus some fixed constant, is known as an arithmetic sequence. So an arithmetic sequence is of the form a sub k is equal to a sub k minus 1 plus d for each integer k greater than or equal to 1. It would then follow a sub n is a naught plus d times n for every integer n. So let's look at another example. We let r be a fixed non-zero constant, and we suppose that a sequence is recursively defined as follows. A naught is equal to some constant a, and a sub k is equal to r times a sub k minus 1. And we are going to use iteration to guess an explicit formula. So again, we start with a naught is equal to a. A1 would be r times a naught, which is r times a. A2 is r times a1, so this is r a, which is r squared a. A cubed would be r a sub 2, so it's r times r squared a, and so this is r cubed times a, and at this point a general pattern has been established. So our guess would be a sub n is equal to r to the n times a. Now, this kind of sequence is known as a geometric sequence. So geometric sequences have the form a sub k equal to r times a sub k minus 1, for each integer k greater than or equal to 1, and it then follows that a sub n would equal a naught times r to the n for each integer n greater than or equal to 0, where this a sub naught, right, is the initial condition. So let's prove a useful properties of geometric sequences, specifically if we sum up terms of a geometric sequence. So for any real number r that is not equal to 1, and any integer n that is greater than or equal to 0, the sum from I equals 0 to n of r to the I is equal to r to the n plus 1 minus 1 all over r minus 1. We will prove this using induction. So the base step is n is equal to 0. In this case, we're going to have the sum I equals 0 to 0 of r sub I. This is just r to the 0, which is 1. Furthermore, we're going to have r to 0 plus 1 minus 1 all over r minus 1. This is just simply r minus 1 over r minus 1, and that's also equal to 1. So the left hand and right hand sides of our property are equal, and so the base case has been proven. Now we suppose that for some integer k greater than or equal to 0, the sum from I equals 0 to k of r sub I is equal to r to the k plus 1 minus 1 all over r minus 1. And what we wish to do is we want to show that it's true for the next integer. That is, that the sum I equals 0 to k plus 1 of r to the I is equal to r to the k plus 2 minus 1 all over r minus 1. So let's look at sum. Well, we can separate off the final term, so we'd be left with the sum I equals 0 to k, then plus r to the k plus 1. Then by the inductive step, the inductive hypothesis, this sum is equal to r to the k plus 1 minus 1 all over r minus 1. Now we need to find a common denominator, so we'll multiply this term by r minus 1. Now distribute this r to the k plus 1 through. This will become r to the k plus 2 minus r to the k plus 1. Well, now we have an r to the k plus 1 here. We have a minus r to the k plus 1 here. They will cancel out. We can rewrite this in any order we want. And so this will simplify to r to the k plus 2 minus 1 all over r minus 1. This is what we wanted. And so by induction, we can conclude that the property is true for any integer greater than or equal to 0. And so that is complete. So we're going to solve using iteration. The recurrence relation m sub 1 equals 1. M sub k is equal to 2 times m sub k minus 1 plus 1. And then we will verify that this solution is correct. So we start as we have before. We start with m sub 1. Now m sub 2 is 2 m1 plus 1. So it's just 2 times, it's just 2 times 1 plus 1. M sub 3 is 2 times m sub 2 plus 1. So this will be 2 times 1 plus 1, and then plus 1. So what we see is that now we get 2 squared plus 2 plus 1. M sub 4, 2m3 plus 1. So it's 2 times 2 squared plus 2 plus 1 plus 1. And so this is cubed plus 2 squared plus 2 plus 1. And a general pattern has formed. Specifically, we're going to have m sub n is equal to 2 to the n minus 1 plus 2 to the n minus 2 plus so on and so forth plus 2 squared plus 2 plus 1. Now, what we want to do now is we're going to take a look at this piece. That can be written as the summation I is equal to 1, 0 rather. No, I'm sorry, it was 1 to n minus 1 I'm sorry, this is 0 of 2 to the I. Right? The reason it's 0 is simply because 2 to the 0 is 1. So actually, we're just writing this whole term as a summation. And then we can say, well, this is geometric. Right? This is a geometric summation. And we drew the property about that. This is going to be 2 to the n minus 1 plus 1 minus 1 all over 2 minus 1. And this will simplify 2 to the n minus 1. And so we take as our guess m sub n is equal to 2 to the n minus 1. Now we just have to prove that this is a solution. That is, we have to prove that our guess is correct. Proof, yes. And as I said, we do this using induction. So we first check the base case for n equal to 1. We would have, and I'm going to rewrite my guess up here. It was a sub n is, I'm sorry, it's not a, it's m sub n is equal to 2 to the n minus 1. So m sub 1 would equal 2 to the first power minus 1, which equals 1, and we check that. That is indeed what m sub 1 should equal. Therefore, the base case holds. So this guess is correct, at least for the first case, for m sub 1. Now, let's suppose for some integer k that is greater than or equal to the base case, that m sub k is indeed 2 to the k minus 1. We now need to show that m sub k plus 1 is given by 2 to the k plus 1 minus 1. So we look at m sub k plus 1. Well, by the recursive definition, that is 2 m sub k plus 1. But by our inductive hypothesis, this m sub k is 2 to the k minus 1. We can now distribute that 2 through. We'll get 2 to the k plus 1 minus 2 plus 1. And this gives us 2 to the k plus 1 minus 1, as desired. Therefore, our guess is correct, and we can conclude that m sub n is indeed equal to 2 to the n minus 1 for all n greater than or equal to 1. So that is how you would go about proving your guess via iteration is indeed correct. Now, there is a problem with this technique. It does require no special tools aside from being able to discern a pattern. Right? So that's an advantage. However, that's also its greatest flaw. A pattern is not always readily discernible. And so other methods would have to be used in this case. There are several methods available depending on how the sequence is defined recursively. In this video, we will only focus on one of these methods. This is the method for solving the class of recurrence relation that is known as a second-order linear homogeneous recurrence relation with constant coefficients, which is quite the mouthful. The definition for it is a recurrence relation of the form a sub k is equal to capital A sub k minus 1, plus capital B, a sub k minus 2, for every integer k greater than or equal to some constant c. A and B are real numbers, with B not being equal to 0. And C is an integer. So the second order here refers to the fact that a sub k depends on a sub k minus 1 and a sub k minus 2. Linear refers to the fact that these two terms appear as separate. Homogeneous refers to the fact that the total degree of each term is the same. And constant coefficients obviously refers to the fact that the coefficients are fixed real numbers. That is, they don't vary with the subscript. So we take a look at these 8 recurrence relations, and we are going to decide which are second order linear homogeneous with constant coefficients. So let's start with A. Well, it's second order. It depends on a sub k minus 1 and a sub k minus 2. It's homogeneous in that they have the same degree. It's linear in that they appear as separate terms, and they have constant coefficients. So A is a second order linear homogeneous with constant coefficients. All right, we look at B. Well, B is not second order. It's third order. So that's out immediately. Let's look at C. We have k minus 1, k minus 2, so it's second order. They're separate terms, so it's linear. They have the same power, so it's homogeneous. And the coefficients are constant. D is second order. It depends on dk minus 1, dk minus 2. However, it is not linear. dk mon times dk minus 2. We look at e sub k. 2 times e sub k minus 2. It's second order. It's linear. It is homogeneous. And has constant coefficients. Right, remember the definition. Right, the only restriction was B was not equal to 0. Didn't say anything about A. So we look at F. Well, it only depends on fk minus 1. So that's not second order. We look at G. It's second order. It's linear. It's homogeneous. And constant coefficients. We look at H. It's second order. It's linear. It's homogeneous. But right here it has a non-constant coefficient. So consider the recurrence relation given here. So this relation is obviously going to be satisfied when each a sub I is equal to 0. Well, such a solution would be called trivial. So let's suppose that it has a non-trivial solution. In other words, let's suppose that for some number t not equal to 0, the sequence 1, t, t squared, t cubed, up to t to the n, and then on so on and so forth, satisfies this relation. Thus, for each integer k greater than or equal to 2, t to the k is equal to a times t to the k minus 1 plus b times t to the k minus 2. When k is equal to 2, t squared would equal a times t plus b, or equivalently, t squared minus at minus b is equal to 0. Well, this is quadratic, and so the values that make it true can be found via the quadratic formula. T would equal a plus or minus the square root of a squared plus 4b, and then all over 2. Now, let's suppose that t is any number that satisfies t squared minus at minus b is equal to 0. Our goal is then to show that it must satisfy the recurrence relation. Multiplying by t to the k minus 2, yields t to the k minus 2 times t squared minus t to the k minus 2 times at minus t to the k minus 2 times b is equal to 0. If we simplify this term will become t to the k. This becomes at to the k minus 1. This becomes bt to the k minus 2, and that equals 0. Now we can just solve for t to the k. We get t to the k is equal to at to the k minus 1 plus bt to the k minus 2. Hence that sequence, 1, t, t squared, t cubed, so on and so forth, satisfies the recurrence relation. And this leads into our next lemma, which says just this. A recurrence relation of this form is satisfied by this sequence if and only if it satisfies this equation. So this allows us to determine a sequence of numbers that would satisfy this recurrence relation. We just solve t squared minus at minus b is equal to 0. That'll get us a sequence that satisfies this relation. Now, because of the importance of this equation here, we give it a special name. It is known as the characteristic equation of the second order linear homogeneous recurrence relation with constant coefficients. So we're going to consider this recurrence relation, and we wish to find all sequences that satisfy it and have this form. So what we need to do is we need to set up the characteristic equation. So it's t squared minus at minus bt, right? This is capital A, this is capital B, this is an implied 1, and this has to equal 0. So we solve this, and we ask, can this be factored? So factors of 2 when subtracted give 1 are 2 and 1. So good, this can be factored. I want to take the minus. So this factors to t plus 1 times t minus 2 is equal to 0. And so we have two solutions. T is equal to negative 1 and t is equal to positive 2. So the two sequences that would satisfy this relation, it starts at 2. No, I'm sorry, it would start at 0, right? 1 t squared. So 1, negative 1, 1, negative 1 cubed, which is still negative 1, right? Then 1, so on and so forth, negative 1 to the n, so on and so forth. I actually don't need those parentheses. So that is for t equal to minus 1. Now for the t equals 2, it would be 1, 2, 4, 8, 16, up till 2 to the n, and then so on and so forth. Now, what do we do once we have these numbers, these sequences? Well, the next lemma will give us the answer to this. If we have two sequences, R and S, that satisfy the same recurrence relation, and if capital C and capital D are any real numbers, then the sequence defined by capital C times R sub n plus capital D times S sub n also satisfies the same recurrence relation. So given two sequences that satisfy the recurrence relation, a linear combination would also satisfy it. So we prove this. We suppose that we have two sequences, R and S, that satisfy the same recurrence relation. Then for some real numbers A and B, we have to have R sub k is equal to capital A R sub k minus 1 plus capital B R sub k minus 2, and S sub k would have to equal capital A S sub k minus 1 plus capital B S sub k minus 2 for every integer k greater than or equal to 2. Now let's suppose that C and D are real numbers and define the sequence A sub n equals capital C R sub n plus capital D S sub n for every integer n greater than or equal to 0. What we need to show is that A sub k is equal to capital A sub k minus 1 plus capital B, A sub k minus 2 for every integer k greater than or equal to 2. Alright, well, for every integer k greater than 2, capital A times A sub k minus 1 plus capital B times A sub k minus 2, just replace the A's with the CR plus DS using the appropriate subscript. Right, so let's group our R's together. So there's going to be a C common. And then we'll group our S's together, so there'll be a D common. But this here is just R sub k, right? And this here is just S sub k. But then this, by definition, would have to be A sub k. And so the sequence A sub n, which is C R sub n plus D S sub n, satisfies the same recurrence relation. And so the proof is complete. So let's go ahead and find a sequence that satisfies this recurrence relation. Well, this is the same recurrence relation from the previous example, except now we have two initial conditions. So from that example, we know that r sub n will be minus 1 to the n. Our s sub n would be 2 to the n. Right? And this will be for all integers n greater than or equal to 0. So a sub n would be some constant times negative 1 to the n plus some other constant times 2 to the n. The idea is we have to now determine these constants c and d, and we do that using our initial conditions. So if a sub 0 is 1, right, so a sub 0 we have c times negative 1 to the 0 is 1, plus d times 2 to the 0 is also 1. So c plus d, this has to equal 1. Then a sub 1, so this would become negative c plus 2d, and this would have to equal 8. Now if we just add these two equations together, the c's will drop out, we'll be left with 3d is equal to 9, which means that d would have to be 3. We then plug this into this first equation, so c plus 3 has to be 1, and this gives you that c is negative 2. So a sub n would be negative 2 times negative 1 to the n plus 3 times 2 to the n. And we could rewrite it as 3 times 2 to the n minus 2 times minus 1 to the n. And this would be our solution. There's no need to prove this, as the previous two lemmas have already proven that this is guaranteed to satisfy the recurrence relation. And so this is summarized in what's known as the distinct root theorem. And the proof of this theorem follows directly from the previous two lemmas. So we can use the distinct roots theorem now to find an explicit formula for the Fibonacci sequence. Right, so you should recall from the previous video that Fibonacci sequence is defined as f0 is equal to 1, f1 is equal to 1, and f sub n is f sub n minus 1 plus f sub n minus 2. So we need the characteristic equation first. So the characteristic equation, t squared minus t minus 1 is equal to 0. We need to solve this when we do so using quadratic. So t would be equal to 1 plus or minus the square root of 1 plus 4 all over 2. And this equals 1 plus or minus square root of 5 all over 2. So we have two solutions. 1 plus the square root of 5 over 2, and 1 minus the square root of 5 over 2. So f sub n would be c times 1 plus root 5 over 2 all to the n, then plus d times 1 minus root 5 all over 2 to the n. The idea now is we have to determine this c and d. So I'll rewrite it over here. So f sub 0 is just c plus d, and that has to equal 1. F sub 1, we're going to have c times 1 plus root 5 over 2 plus d times 1 minus root 5 over 2, and this must also equal 1. So what we need to do is much like in the previous example, elimination. So let's cancel out this d. How do we do that? Well, we're going to multiply this term up here by negative 1 minus root 5 over 2. So that'll give us, when we add them together, c times 1 plus root 5 over 2 minus 1 minus root 5 over 2. And that would have to equal 1 minus root 5 over 2. If we simplify this, we're going to get c times the square root of 5 equals, now simplify the right hand side, and we get 1 plus the square root of 5 over 2. And so c would be equal to 1 plus the square root of 5 all over 2 times the square root of 5. Well, this means that d would be 1 minus 1 plus the square root of 5 all over 2 times the square root of 5, which is equal to negative 1 minus the square root of 5 all over 2 times the square root of 5. Therefore, our formula f sub n is 1 plus the square root of 5 all over 2 root 5 times 1 plus the square root of 5 all over 2 to the n. Then it would be minus 1 minus the square root of 5 all over 2 times 2 square root of 5, 1 minus root 5 all over 2. We can actually simplify this even further to the n, right? So typically what we'll do is we'll write, and I'll write it up top here, f sub n is equal to, pull out that 1 over root 5, then notice we have 1 plus root 5 over 2 times 1 plus root 5 over 2 to the n. So we have 1 plus root 5 over 2 to the n plus 1. And then we do the same thing for the second term. So we'd have 1 over root 5 times 1 minus root 5 over 2 to the n plus 1. So this up here gives us our nth Fibonacci number. So now we consider the recurrence relation again, except now let's suppose that the characteristic equation has only a single root. Then one sequence that would satisfy it would be 1 r squared, r cubed, r to the n, where r is that single root of the characteristic equation. Another sequence that would satisfy it would be 0 r, 2r squared, 3r cubed, so on and so forth, n r to the n, so on and so forth. To see this, observe that since r is the unique root of the characteristic equation, the left-hand side can be written as t minus r squared. So t squared minus at minus b is t minus r squared, which is t squared minus 2rt plus r squared. by comparing the coefficients, we observe that a is 2r and b is negative r squared. So we define a sequence n r to the n, then plugging it into this equation, we have a times k minus 1 times r to the k minus 1 plus b times k minus 2 times r to the k minus 2. This would be 2r times k minus 1 times r to the k minus 1 minus r squared times k minus 2 times r to the k minus 2, which is 2 times k minus 1 times r to the k minus k minus 2 times r to the k. Simplifying this, we get k times r minus k, which equals s to the k. Thus, the sequence given by Sn equals n r to the n satisfies this recurrence relation. So our lemma, let a and b be real numbers. Suppose the characteristic equation t squared minus at minus b is equal to 0 has a single root. Then the sequences 1, r squared, r cubed, up to r to the n, and 0, r, 2r squared, 3r cubed, up to n r to the n, both satisfy the recurrence relation a sub k equals capital A times a sub k minus 1 plus capital B times a sub k minus 2 for each integer k greater than or equal to 2. And so our single root theorem basically says that given a recurrence relation a sub k equals a sub k minus 1 plus b a sub k minus 2, whose characteristic equation has a single root, then the explicit formula is given by a sub n equals c r to the n plus d n r to the n. And again, this follows directly from the previous theorem, the previous lemma rather, and one of the other lemmas we studied before. So let's go ahead and solve this relation. So first thing we do is set up our characteristic equation. So we get t squared minus 4t plus 4 is equal to 0. This will give us that t minus 2 squared is equal to 0. And so t is equal to 2. So our explicit formula will have the form c times 2 to the n plus d times n times 2 to the n. Now we use the initial conditions. So b sub 0 would be c, and then this pc would just be 0. So c is equal to 1. B sub 1 will get 2 times c plus 2 times d. But remember, c is 1. So this is 2 plus 2 times d, and that has to equal 3. So 2 times d is equal to 1, and so d is equal to a half. Therefore, our explicit formula is b sub n is equal to 2 to the n plus 1 half n 2 to the n. If we factor out that 2 to the n, we'll have 1 plus n over 2 left over, and so we can take this as our explicit formula. As I said, there are other methods, however, those are left for more advanced courses. This is all I want to study in terms of solving recurrence relations in this course. So that concludes solving recurrence relations.